Hello, everyone. Thanks for joining me again today. I hope you had a lovely weekend. Time to start another week. And I know that during our previous session, I said I would probably want to focus on fleshing out this naive parser and maybe start fishing out some properties from the strings provided by the tokenizer. But I did some research. Research. I spent 2 minutes reading through Happy parser generator documentation, and it's not looking that scary. It looks very similar to what we saw in Alex. So I think we've already proven that we can connect the three pieces together: the lexer, the parser, and the renderer. And I'm not in a hurry to make it perfect using the naive parser. So the concept is kind of proven already of parsing my proposed Wyvern syntax. So I think it would be a good time right now to introduce Happy into the mix and to replace my naive parser with Happy. So I hope you have your drink of choice ready. I have my coffee here. And before we start experimenting with Happy, let's do a little bit of cleanup. Introduce Alex. Yes, we have introduced Alex a long time ago. Let's try to close that issue. Mm-hmm. So today's session is probably going to be very slow-paced, exploration-based. Mm-hmm. So let's introduce a new file called parser. Let's call it parser P. Simple expression syntax consisting of integers, variables, and operators. It's an optional module header, which is just a Haskell module. Mm-hmm. So let's call it parser. Declarations. Calc, this is probably going to be changed. Token type, let's change it to string, because I'm tempted to change it to string, but the example calls for a token, which is probably going to be a custom type. Let's see. The first line declares the name of the parsing function that Happy will generate. In this case, it's calc. So this is not the case. In our situation, we will need a diagram. Token can say the parser, i.e. the function calc, will be of type token, a list of tokens to t, where t is the return type of a parser. The error directive tells Happy the name of a function it should call when an event of a parser. More about this later. Okay. Now we declare all possible tokens. Okay. So in our case, In our case, we only care. You know what? I need to keep resisting the temptation of changing the token type to just string. Okay. In my humble opinion, it looks a little bit better. Let's see if this works. The symbols on the left are tokens, and they will be referred to in the rest of the grammar. And to the right of each token closed in braces is a Haskell pattern that matches the token. The parser will expect to receive a stream of tokens, each of which will match one of the given patterns. The definition of a token data type is given later. Okay. The $$ symbol is a placeholder. We don't have it yet. That represents the value for each token. Oh yeah, sorry, we do have it here. Like yak, we include %% here for no real reason. What? But I don't see it. Now we have the production rules for the grammar. So this is the interesting bits. You have all the expressions. You know what? Let's change it to calc. Okay. We have expression. Let var equals expression and expression. Expression 1 plus minus. Oh, sorry, this is let expression. A plus minus term times divided factor int var bracket. Each production consists of a non-terminal symbol on the left, followed by a colon, followed by one or more expansions on the right, separated by a pipe. Each expansion has some Haskell code associated with it, enclosed in the braces as usual. So these are the constructors, I think. But we are still missing these types. The way to think about the parser is with each symbol having a value, we defined the values of the tokens above, and the grammar defines the value of non-terminal symbols in terms of sequences of other symbols, either tokens or non-terminals, in a production like this. And combined with t_1 to t_n, that's e. Whenever the parser finds the symbol t1 to tn in the token string, it constructs the symbol n and gives it a value of e. Okay, which may refer to the values t1 to tn using the symbols $1 to $n. The parser reduces the input using the rules in the grammar until just one symbol remains. The first symbol defined in the grammar, namely expression in our example, the value of this symbol is the return value from the parser. To complete the program, we need some extra code. The grammar file may optionally contain final code section enclosed in curly brackets. So this is the grammar. So let's call it G. All parsers must include a function to be called in the event of a parse error. In the error directive earlier, we specified that the function will be called in parser. Okay. So we need this. Parse error. Note that the parser must be polymorphic and its return type, which usually means it must be a call to error. We'll see in monadic parsers how to wrap the parser in a monad so that we can do something more sensible with errors. It's also possible to keep track of the line numbers in the parser for used in error messages. This is described in line numbers. Oh, we'll get to that. Next, we can declare data types that represent the parsed expressions. Okay. And the data structure for the tokens. Okay. And a simple lexer. I'm just taking this as face value, and I think it would be sensible for today, just to make it our goal to let the example compile and run. And finally, a top-level function to make some input, to take some input, parse it, and then print out the result. So here, and that's it. A whole lexer, parser, and grammar in a few dozen lines. 103 to be precise. Another good example is Happy's own parser. Several features in Happy were developed using this as an example. To generate the Haskell module for this parser, the command happy example y. So this is, even though it's a grammar file, the suggestion is to give it a y extension. Okay, so we don't have Happy installed. Let's see how to install it. Cabal install Happy. Happy. Oh, that was easy. That was pretty simple. Happy example y. So in our case, this is a parser, but okay. With Happy 2.0, the GHC flag has become non-optional. To suppress this warning, pass the GHC flag. Okay. Parser 22. So there's a parser error in the parser. Is it because we're missing this? Yes. Okay, so the parser code is generated. It looks absolutely delicious. I'm not touching that. Okay, we have the parser code. Let's see what happens next. The Haskell module will be placed in the file named example.hs. In our case, it's parser.hs. Additionally, invoking the command happy example will produce the file info, which contains the detailed information about the parser, including states and reduction rules. Okay, that could be a little bit too much for now. So all we need to do now is just to call it. We need to expose function main. Parser. That's in base. Why is this a parser problem? Let's go to line 15, see what happens. Let's see. How do you see here? Okay, so let's try to compile the parser on its own. What happens if we do this? Let's Google filter for this problem. We do have base. Oops. Is this the problem? Mm-hmm. This will teach me to never change anything from the example, even if it's something that I think it should work. Ooh, I think I should update base. Let's see. Okay, I think I'll let it finish installing off camera, and starting next session, I'll try to shave off some of this code to make it fit our current very simple Lexer. So no tokens required yet, I hope. In the meantime, let's allow it to finish installing, and maybe off camera I'll fix that import error. Right. I would like to thank you all for your attention today, especially on a Monday. And I would like to wish you all a fantastic day ahead. Take care.